So we have now the next talk. We have Beng Xiu from the University of Hong Kong. She is a final year PhD student, so she might be on the job market soon. And she's going to talk today about her work on revisiting RDMA reliability for lossy fabrics.
Should I use this one?
Either one is fine.
Okay. Okay, thank you. Good morning, everyone. I'm Wenxue Li from Hong Kong, UST. Today, I'm very happy to have this opportunity to present our recent work on revisiting RDMA reliability for lossy fabrics. This work was done during my internship at Huawei Hong Kong, and it's a joint work with many co-authors. First of all, I would like to introduce the landscape from lossless RDMA to lossy RDMA. As shown here, in 2015 or 16, almost all data centers use the lossless RDMA solution. This solution simply adopts a go-back-N retransmission mechanism in the RDMA NICs and relied on PFC or CBFC to ensure a lossless underlying fabric. However, the deployment scale of lossless RDMA networks is restricted. The reason is that the coarse-grained link level flow control, for example, PFC or CBFC, causes several performance issues. For example, head-of-line blocking, congestion spreading, and deadlock, and significant switch buffer overhead. Because of this problem, the deployment scale is limited. Therefore, since 2018, both industry and academia have been exploring efficient RDMA transmission over lossy fabrics. Up to now, almost every leading company has its own customized lossy RDMA solution, and we have also been working in this direction. The state-of-the-art lossy RDMA solution called RNIC-SR implements a simplified selective repeat mechanism, or SR for short, in RNICs to enhance the loss recovery efficiency. However, even with RNIC-SR, performance issues persist in lossy fabrics. First, RNIC-SR assumes single-pass transmission with ECMP as the default load balancing scheme. However, ECMP hashing collisions are inevitable, and they cause significant throughput degradation. The impact is especially pronounced in today's AI workloads. Packet-level LB methods, such as packet spree or adaptive routing, are promising alternatives to ECMP. However, RNIC-SR is natively incompatible with packet-level LB. The root cause of this incompatibility is that packet-level LB can cause out-of-order packet arrivals even when there's no packet loss, while RNIC-SR assumes that all out-of-order packets are due to packet loss. As a result, combining packet-level LB with RNIC-SR leads to excessive spurious retransmissions. For example, if P4 arrives before P2 and P3, the receiver will request the sender to retransmit P2 and P3. Second, certain lost packets cannot be recovered through fast retransmission in RNIC-SR. Specifically, the RNIC-SR requires a SAC to trigger the loss recovery mode. As a result, if the tail packet of a flow is lost, no SAC is generated. This prevents recovery through fast retransmission and instead relies on a retransmission timeout, or RTO for short. Additionally, to avoid retransmission ambiguities, the sender enters loss recovery mode only once and remains in this state until it exits. The sender exits loss recovery mode only when it receives a packet with EPSN greater than the largest PSN of outstanding packets. As a result, if the retransmitted packets are dropped again, they can only be recovered through an RTO. The increase in RTO events can significantly degrade performance. So based on the above analysis, we aim to revisit RDMA reliability with the following objectives. First, independence from PFC. The proposed solution must eliminate the dependence on PFC to completely avoid its drawbacks. Second, compatibility with packet-level LB. The proposed solution must be inherently compatible with packet-level LBs, which requires accurately distinguishing real packet losses from out-of-order packet arrivals. Third, the ability to quickly retransmit any lost packets. And finally, a hardware-oriented design. The proposed solution should adopt a hardware-oriented design, making it feasible for unique offloading and ensuring low memory and processing overhead. We propose DCP, a transport architecture consisting of DCP RNIC and DCP switch. Conceptually, DCP defines the data plane, DP for short, for payload transfer, and the control plane, CP, for header transfer, while lossless RDMA ensures that both DP and CP are lossless via PFC. DCP switch only ensures a lossless CP while allowing the DP to operate in a lossy manner. The key design idea of DCP is to leverage the lossless CP feature to enhance the RNIC reliability, mainly in packet retransmission, packet reception, and packet tracking. This table summarizes the difference between DCP and its closely related works. DCP is the only one that fully meets the four requirements. First of all, I would like to talk about the lossless control plane. DCP switch implements a packet trimming mechanism similar to previous works, specifically when there is no congestion, indicated by a relatively low queue length. The entire data packet is enqueued into the normal queue, also called the data queue. When the data queue's length exceeds a given threshold, the switch trims the payload from the packet and goes to step 2. In step 2, the switch modifies the DCP tag in the remaining header and enqueues the header only, or HO for short, packet into another queue, also called the control queue. To ensure lossless CP transfer, the switch uses a weighted round-robin, WR for short, scheduler to prioritize the control queue. By configuring WR weight properly, we can guarantee that the control queue remains lossless. Okay, how can we utilize the HO packets for loss recovery? Let's first consider a straightforward HO-based retransmission solution. Upon receiving an HO, the sender side RNIC fetches the corresponding U key and processing it, then fetches the data and finally encapsulates the data into a packet. This idea is simple to come up with, but it has two issues. The first issue is inefficient retransmission. It requires 2 PCIe RTTs to finish a single packet, which is quite inefficient. The second issue is incompatibility with the CC module. Since HO packets are stateless and independent, if we immediately retransmit upon receiving an HO, the retransmission rate becomes tied to the arrival rate of HO packets. We therefore propose our efficient HO-based retransmission approach. We incorporate a retransmission queue or retrans queue for short in host memory for each QP. On the RX path, upon receiving an HO packet, the RNIC extracts some metadata from the HO, packaging it into a retransmission entry and writes this entry. Actually, it's a data structure into the corresponding QP's retrans queue. Note that this retrans queue is exclusively managed by the RNIC, so this does not involve any software overhead. In the TX path, we employ a batched fetching approach. After checking whether the retrans queue is empty and getting credits from CC, the RNIC fetches multiple retransmission entries and U keys from retrans queue and SQ respectively. After performing address translation, the RNIC fetches and encapsulates multiple packet payloads, and finally, it updates the CC status. So in summary, our approach improves PCI utilization and enables CC's controlling on the retransmission rate. Now, since load balancing can lead to out-of-order packet arrivals, the question is, how do we handle them? A feasible way is to allocate a very large reorder buffer in the RNIC or in host, where the out-of-order packets are temporarily stored. Once all packets are received, the RNIC or host reorder them and push them into application memory. However, this approach introduces significant memory and CPU overhead. To address this issue, we choose to extend the standard RDMA header, allowing the RNIC to write all packets, whether in order or out of order, directly to the correct locations in application memory. This eliminates the need for a reorder buffer. This kind of header extension is a kind of common approach adopted by many protocols, so I won't go into the details. Another question is that how do we track which packets have been received or lost? Usually we use packet-level bitmaps. However, bitmap introduces trade-offs between memory overhead and processing efficiency. One approach for maintaining bitmap is to pre-allocate a fixed length, typically BDP-sized bitmaps for all active QPs. This method has constant packet processing latency, which is good, but its memory overhead is high, and it often wastes a lot of space. Another common approach is the linked trunk method. Each QP is pre-allocated with only one trunk, and is linked with additional trunks as needed. This approach improves memory utilization. However, as the out-of-order degree increases, access latency also grows. This is because accessing a bit in the nth trunk requires n steps. So we propose a bitmap-free packet tracking approach to break the trade-offs. It's based on the exactly once feature. Our HO-based retransmission ensures that only truly lost packets are retransmitted. So for any given packet, exactly one copy arrives at the receiver. Based on this feature, the receiver-side DCP RNIC tracks message-level information using packet counting, rather than tracking at the packet level. It maintains a multi-bit counter for each message. Upon arrival of a packet, the corresponding messages counter is incremented by 1. When the packet counter equals the message size, the receiver determines that this message is complete. Note that this exactly once assumption may be violated due to link failure or accidental HO packet losses. To handle these extreme cases, we develop a customized timeout approach as a fallback. If you are interested, you can refer to our paper for details. Finally, I would like to talk about the combination of design modules. Ideally, all of our design modules should be used together. However, it's important to note that this bitmap-free packet tracking relies heavily on the exactly once feature. Therefore, in environments with very frequent failures, this approach may not be suitable. In fact, this bitmap-free design is orthogonal to the rest of DCP RNIC's architecture. This means traditional packet-level bitmaps combined with the remaining components of DCP RNIC we propose also function correctly. We implement the lossless control plane using a Tofino2 switch and build a fully functional prototype of DCP RNIC using an FPGA board. We implement DCP RNIC by modifying specific modules based on an FPGA-based RNIC go-back-N baseline prototype. We evaluate the basic performance of DCP RNIC prototype. It successfully maintains hardware offloading capabilities, achieving throughput and latency comparable to RNIC  both of which outperform DCP significantly. we conducted extensive testbed experiments. The testbed is shown here with 2 Tofino 2 switches and 16 servers. We used several benchmarks to demonstrate that DCP achieved superior loss recovery efficiency. DCP is natively compatible with packet level LB, with adaptive routing, or AR for short, as the representative in our experiments, and DCP provides benefits for AI workloads. We also conducted comprehensive simulations. The topology is a 2-layer cloud network with 256 servers, and all links operate at 100 gigabits. We validated that DCP performs well in cross-DC scenarios, even with relatively small switch buffers. In contrast, the lossless solution requires much larger switch buffers and still perform poorly. We also show that DCP benefits from CC under high-load scenarios, and that DCP plus CC achieves the best performance in these cases. Finally, we compared DCP with RAC-TLP and timeout-based solutions, and show that DCP outperforms it. Finally, I would like to conclude the talk. In this paper, we present DCP, a transport architecture that rethinks RDMA reliability for lossy fabrics by leveraging a lightweight lossless control plane in switches. DCP enhances the RNX reliability, enabling compatibility with packet-level LB, precise retransmission, and minimal memory and processing overhead. Our prototype and evaluation show that DCP significantly outperforms existing RDMA solutions, advancing the practicability of high-performance RDMA over lossy fabrics. Thank you. That's all. I would be happy to take any questions.
Thank you for the fantastic talk. Any question?
Yes. Just wait a second. I'm going to get the microphone to you. Okay.
Hello, thank you for your talk. My question is that for the lossless control plane, how is pausing or PFC-like measures are taken to ensure that the queue is actually lossless? And the second is that for unrecoverable packet losses, such as maybe link failures in the network, how will the timeout affect the performance? As we see in nowadays data centers, there are high probabilities of failures happening in the network.
Your first question is how DCP switch ensures a lossless control plane, control queue?
Yes, is PFC involved in this?
Yeah, actually our DCP switch ensures a relatively lossless control queue using WRR weight. It assigns a higher weight to the control queue instead of data queue. So the control queue gets a higher priority when draining the packet. And we prove in our paper that a proper weight can ensure a lossless CP even with largest local incast burst. So that's the first answer. And the second one, we consider, in this paper, we target congestion loss. So we use packet trimming to handle the loss recovery. We think the link failure or some extreme cases are not very common because the optical transceiver or link, they provide a bit error guarantee. So actually there's not very much that kind of packet loss. And we also provide a timeout, a customized timeout to handle these cases, but it is obviously not very efficient. So we still rely on HO-based retransmission to handle the congestion loss, and we assume there's not so many link failure caused losses.
Okay, thank you.
Thank you. I think there is one more question over there.
Yeah, for another question, packets can drop for other reasons than the queue field. So how do you handle those kind of silent packet drop? How do you detect that and do the retransmission?
You mean you want to know more about access?
Yeah, I mean, you have two queues that only handle the reason for packet drop is because packet is filled, right? Queue is filled. But there are other, many other reasons a packet may lost.
Yeah, as I answered before, we only target congestion loss. In this paper, we actually didn't pay much attention to losses caused by link failure, switch failure, or bit error. We incorporate a timeout mechanism to handle these losses. It is similar with the go back in retransmission. So yeah, I think this kind of losses is not very common. So we actually didn't pay much attention to this kind of loss.
Okay, thank you.
Okay, so I think we are at time, so let's thank again the speaker, and we can go to the next talk.
Thanks.